Sub-circuit. Sub-circuit is like when you have a circuit hierarchy. This is the module name A and module name A include B and C, etc. Sometimes we get the module A, B, C, D, D at the same hierarchy with the B, something like that. In such case, we define the sub-circuit. So for example, for this kind of circuit, each inverter has the PMOS and NMOS inside. So this kind of instance is the sub-circuit. So we define that inverter with the sub-circuit definition, starting with the dot sub-circuit. The sub-circuit need to have an input and output. So input port information here, and this is the property we want to pass on to the sub-circuit. So we have inside the sub-circuit, we have M1 and an M2. So YA is the network we are seeing. Get the ports, we have the MMOS and PMOS, and all these kind of information are defined in sub-circuit with the dot ends. This is the example of the fan out of 4 inverter delay for simulation. So we use the sub-circuit definition. We are going to use that, and shaping we can change the size information, passing through some device size information that will change the loading, right? We'll see it later. Continuing here, 3, 4, 5 different inverter defined with the larger multiplication factor there. We have a transient definition here. We have a measure here. So actually our delay measurement is done on the X3 block. So for example, you have a X1 and X2 and X3. This is just something that we want to actually measure. X4, X5 for example. So when you make the step input there, the step input rise time is too fast. You will take time, several buffer stage to settle some finite rise time. So if you look at each node's output, this is the actual delay output. So we have A, B, C, D, E, F. A is the input, right? A. And B is here. B, C, D, E, F, right? So we have in this example we applied like a little realistic rise time, right? That is similar to the internal output. Here is a little faster, a little slow down and slow down, right? Finally it slows down, right? Compared to here and there, this slows down practical with the number. So we measure this passing half VDD, 2 points, right pole. This delay is measured each. So optimization. So lec7Spice has the capability to adjust parameter automatically. So that's the Here is the optimization example. Here, parameter P1 is defined with optimization range between search for 4 to 6. The initial guess is 8. Right, you will try to find the model optimum, the maximum 30 iteration here. So you compute best ratio parameter. So from the previous example, we can find that the pin ratio for equal rise and fall delay is 3.6 to 1. So PMOS is like a 3.6 times larger than the 3.6 times larger. This is for the minimum delay to achieve, right? This results in very big PMOS size. This typically very waste of the power too. So in actual, so sometimes if you need the equal delay, then you can design like this. But in actual, the standard cell design provided by the foundry, they use the lowest average delay. I mean the rise delay, and so average delay, the average delay is d rise and d fall of the average. So they don't know what event will happen, whether that will be rise output or that whether the output will be fall. So what the in statistically what it matters is the average delay is minimized. So if you find the average delay is minimizing the ratio, PN ratio that minimize the average delay is 1.4. So for example, even though the rise time is slower than the fall time, this give us the average 73 picosecond delay. So this is actually most popularly used in actual typical the standard cell design ratio. But when you do the most of the custom design, you may choose differently. So depending on the actual design specification, you can choose whether you will get the larger equal, whether you will choose equal delay or whether you want to list the average delay design. This is better for the low power. If you care for the actual performance, you may go for the larger PN ratio at the expense of more power. So this is one setup that we can measure the logical effort. So the third one is actually the device under test. As I mentioned, that we put some additional input gate to shape the input properly. So input rise time is properly settled at there. And each stage we have a fan out of H. So typically, ideally, for the fan out of H, we get the same delay. And also we have a load setup, fan out load H, right? And also we put additional load, because when the load doesn't, if the load doesn't have the output, then you will have the faster output edge that will affect the input edge, right? The input edge rise and fall time. So the input edge will be affected by the output sharp edge, because if there is a parasitic capacitance always there. So this prevents us from measuring the proper delay on the device on the test block. So as you can see, whenever you build some test measurement, you have to always, this is always very important, always to model the input properly and output load condition properly. So without having input and output shaping the block, that you will get the wrong data, a wrong simulation result. This is very similar to analog circuit design. For example, when you have an amplifier design, even in analog, most of students assume that ideal voltage source going into amplifier, and then there's no load specified at the output. This actually cannot properly simulate the amplifier characteristic. You must use the practical input resistance, because the the previous driving amp will have a finite output resistance, so you have to put some resistance there and signal coming in. Also, you have to put some capacitance there, because the driving inverter will have a input parasitic capacitance there. You have to, or load capacitance. You have to properly model input and output network. So both analog and digital circuit design methodology, you have to be very careful about modeling input and an output load, right? Otherwise, you will not get accurate simulation result. This is the logical effort. So we plot the simulation result, the delay versus the fan out of H to this point. If you increase the fan out, you get the increase the delay. So this is straight line there. We can see that this point is parasitic, this y-intercept point is parasitic delay, right? P. The slope of this guy is the logical effort G. So delay can be dAbs, is represented by G times P, H plus P, right? The linear approximation. So this is the ABS, here the absolute delay in picosecond, right? Okay. So this is the simulated NAND gate logical effort for the input, 2-input NAND gate and 3-input and 4-input NAND gate. We have a different input and different rise and fall logical effort. Those are different, because the circuit itself is not symmetric. So for example, if we 2-input NAND gate, we have A, B, and A and B. So A is on the top for the pull down network, A is on the top and B is on the bottom. So for example, for rise time logical effort, we have A has a larger than B, meaning the A input is slower for the rise time, because when the A input changes, we want to, let's say A from high to low, change as 1 to 0 transition, we want to pull up the output, but the A is close to the output, so there's a coupling capacitance there, parasitic, that will actually, so the output want to move up, but the input falling edge coupled to the output, it make it actually slower. So for the rising logical effort, A input is larger and slower. But for the falling logical effort calculation, the A is faster, because for the A will just need to pull down the output capacitance, but for the B, you need to pull down this internal parasitic capacitance as well, because according to the Elmo delay, right? So it sees more capacitance there for the B input. So, but eventually, when you take the average parasitic delay there, or the input A is slower, right? The input B is faster. You can say that, right? So the parasitic delay is greater for the outer, the input, right? And also we can find the average logical effort for the rising and falling, right? By taking average of those, right? So it's like this, right? So actual average logical effort is better than estimate what we just calculate by hand, right? Then the number we calculate by hand is a little larger than the actual simulation result. This is the comparison for the all different process we test here, different feature size F. It had all different supply voltage here. The fan out of delay is scaled down for better process, right? So approximately 180 nanometer process is compared to 350 nanometer, we get the almost 2x larger, smaller speed. About it at 2.5x lower, faster, something like that. So the feature size actually scales the delay similarly, right? But for 250 to 180, the tau is like 2x faster here. But what you see is the supply doesn't scale as much. It just stay 1.8 high, so we cannot directly compare the speed versus the feature size. All the factors, supply and other thing also matter, so that roughly it just meet. So for example, 600 to 250, around 2x faster, right? Here, let's say for the logical effort for inverter, we specify that inverter logical effort is 1, and different logic gate, we say that NAND 2 is the second best always, right? Second best, close to the inverter, right? Then logical effort. So NAND 2 is is fast. For the parasitic delay as well, we see that NAND 2 is also fast compared to other logical logic block. So inverter, we have a parasitic delay a little larger than logical effort. So a little larger than 1. See, this is something that we can see the trend here, right? Definitely NOR is compared to NAND is a lot worse than NAND 2. So when you design a logic block, you just use inverter and NAND 2. That's kind of a way to design the faster building block. So any building block, for example, let's say, or whatever like this logic is required, then you can always convert that with the NAND gate and inverter by using bubble pushing technique, right? You can change the shape, the OR gate to AND gate by inverting input and output like that. Also here, change the polarity of the input and output. That becomes the equivalent circuit, right? Bubble pushing. So you make equivalent in logic gate, and then from there you add the inverter like this. So here this inverter goes away, disappear, and like this, an inverter here, something like that. You can have now we have a NAND gate here, NAND gate, inverter there, and then you put the inverter there like that. You can always transform the logic with the NAND gate and inverter, right? So it is useful to construct any logic you want, right? Even the inverter can be constructed with the NAND gate. The NAND gate, if you are lazy and you don't want to design anything, then you just put inverter to input inverter and tie the input together. That will equivalent to inverter, right? Stuff like that.